Last one, catalysts. These increase rates of reactions, but they do not, they don't get used up, and they're never, they never make a reaction that wouldn't happen spontaneously occur. So if the reaction wouldn't happen in nature, it's not going to happen. All it does is increase the rates of that reaction occurring. So no non-spontaneous reactions. Better way of saying that. Only reactions that occur in nature. So it only speeds up those reactions that would already happen. How does it do it? How do they function? So if we look at those reaction coordinate diagrams whenever we did endergonic and exergonic reactions, this is an example of an exergonic reaction because our product's energy is lower than our reactants. Okay, this is the amount of energy. Let me switch colors. This is the amount of energy that was lost during this reaction. But we don't really care about that. What we care about is, for enzymes, this energy. So this energy between where the energy levels of the reactants are and this highest point in this energy diagram, this is called the activation energy. So this is the energy barrier that you have to reach or get over for this reaction to occur. So nothing's just going to happen. Something has to, you have to do something. We're not going to go into activation energy too much. We talked about that in a few videos ago. But all you need to know is that an enzyme is going to take this activation energy and change it to maybe here. So because you don't have to put in as much energy, once you hit this threshold, the reaction occurs, which means since it doesn't have to have as much activation energy, it can increase these rates. Okay, so these are functioning as biological catalysts. They're making reactions happen faster. They force collisions between molecules. That's another way to think about them. They're acting in both anabolic and catabolic reactions. So you need to put something together, an enzyme can help. You need to break something apart, an enzyme can help. Enzymes are always going to be working as long as there's substrate or reactants present. So as long as there's a reactant there, or a substrate there, substrate's another word for that, the enzyme's going to keep working. But enzymes are specific to certain substrates. So let's just say this is my enzyme, okay, and here is my substrate. So the enzyme is going to have an active site for this substrate. Boom. So this guy can come right in here, and then he'd just fit like that, and this enzyme would be good to go, making this chemical reaction happen faster, whatever it's doing. But the whole point is it can only take this substrate. It can't take this substrate, and it can't take this substrate. And the reason is that when we say these active sites, they're highly specific. So these enzymes have a high specificity for the substrate that they work on. They can't work on everything, only the things that can fit in their active sites. And this has to do with the different molecules and chemical interactions that are going on at an even smaller level than this. Okay, how can we make an enzyme stop working? So we call this enzyme denaturation. What is denaturation? It is the loss of a protein's 3D shape. So a good question to ask, what level of organization for proteins gets affected whenever an enzyme is denatured? Well, if the loss of the protein's 3D shape, if you remember what step 3D came in, it was that tertiary structure. Okay, so primary structure is not going to get affected because it's just this string of enzymes, string of amino acids. Secondary structure is not going to get affected because of these interactions are still holding it together to be this nice helix. But if you increase the temperature, Then the thing, remember, the thing that's keeping this in a tertiary structure is where we said something like this part of the helix, this part of the helix was attracted to this part of the helix, so it was able to come over there and fold. Once you get to a certain heat, whatever this attraction is right there, the heat is too strong. It breaks the bond of whatever is happening during this interaction. So to denature an enzyme, you typically do it by bringing it to a really high temperature, or you can change the pH, because when you change the pH, you change charges, and then that affects this interaction just like heat does. So the whole point is, when you denature an enzyme, it loses its 3D shape, which means it's lost its tertiary structure, which means it's lost its active sites, which means it cannot work. So enzyme denaturation, lots of proteins 3D shape, typically due to high temperatures and a change in pH. Enzymes have a homeostatic range or homeostatic window for where they optimally work as well. So if you get out of that, they're just not going to work.